thing last 2 weeks ago, so I was happy about that. Opioids, and Dave promises to watch it pretty soon. So, yeah.
Let us know, Dave.
We're good? We're going? All right. Happy Science Sunday. We've got some people in the stands here cheering us on, and you out at home maybe, so if you're watching us right now live, you can send in questions and we'll try to get them answered and go on from there. Thanks so much for tuning in, and thanks so much to folks that have come in. It means a lot when you're here for our talks. I just wanted to report, I know I had sent something out to people that are on my email strand, that I went to the Southside Science Festival. It was their first year doing it down at Hyde Park, right on the campus of University of Chicago. And it was very enthusing. It really, really was special to be there. I'd say there were probably 500 people in this little quad area on the campus of University of Chicago. And people from Fermilab, people from Argonne, all these young college-age kids that were all University of Chicago students with all 16 different tents of demonstrations. They were rolling up little strands of paper and making pillars that could take whole college textbooks on them and things like that, showing the strength of materials. And there was some physics and geology. A guy was there with a bicycle wheel, and kids were holding the bicycle wheel, and they could see that if it was spinning, Bob, this is kind of up your alley, if it was spinning, then they were sitting in a chair, and they was turning around when they do it different directions, and so showing a lot of angular momentum forces and different things like that. A group was extracting DNA from strawberries, and with the kids, and then there were the whole community of kids. A lot of Southside kids and families were there too. And they were just so enthused about science, so I was really glad I went, and it was a nice charge to my system to see so many people out in the world in Chicago that are enthused about science. So hope that you keep your enthusiasm for science too. I just wanted to make sure I reported about that. I am also heading out with some people from this church congregation and some others. I'm going to be in Venice in about a week and a half. And we're visiting in Venice for a few days, and then we're taking a barge tour up the Po River, which we were pretty concerned about with drought. Might have been pretty dry, but apparently it's not been that bad. But we're going to be riding around in Italy in time. So Scott, you got the whole bag. You're holding the whole enchilada for the next few weeks, and I'll be back in mid-October.
That could be messy if there's an enchilada in a bag.
Yeah, they have them that way. You can get them that way. So we also, I know I made sure we had a microphone available, so folks that want to ask questions later on, if you make sure we use a microphone, then the person up front won't have to repeat the question that you ask or the comment that you have to make about it too. But welcome to Science Sunday. Thanks for coming out here. Scott is going to talk about the beginnings of science or the meanings of science, and I want to turn it over to him. So.
Thank you, Mike. Hello, science lovers. It's nice to be back for another season of Science Sunday.
Yes, yes.
This is your 12th year?
I believe it is.
Wow. Seems like just yesterday that what was something about riparian ecosystem is something, that was one of your first, wasn't it? Or wait, did you have a guest speaker, or am I misremembering completely?
Some of the first ones we almost had some demonstrations. I did some batteries and bulbs, and people were making connections and trying to get with one wire and a bulb and a battery, trying to see how to light them up. And so some levels of science, more of a experimental discussion kind of tough stuff with that way.
I'm thinking about one of the Science Sundays I'll do this year is the distinction between theoretical, observational, and experimental science, and might bring in a couple of demos for that as well, like reproducing one of Galileo's famous experiments. I've been thinking about that. Although we don't have the Leaning Tower around here, so I'm not sure how that'll work.
Which was really interesting for me just yesterday, seeing all these different demonstrations and experiments set up for kids. They were taking thumbprints and putting them under certain chemicals and getting different analyses and so on. It was just a whole variety of amazing science. It was a lot of fun.
Wish I could have joined you. My husband and I are currently dog sitting a very ill dog, so we just can't really get away for a day, but sounds like it was a lot of fun.
Yeah.
All right, well, I'd like to kick off the year, my first talk, kind of with some foundational issues about definitions of science, the philosophy of science. And I believe the DuPage Unitarian Church this year, or at least this month, is focusing on ideas of community and society. So I thought I would give some time to focus on the notion of the social aspects of science, which I will get to eventually. But first, I'm going to read experts. I'm going to read expert opinions, expert excerpts.
Expert excerpts.
From a book I have that has some information about philosophy of science. Long before written records, and prior to the birth of any extant language, there were wandering people. Likely they followed the bounty of the seasons. These wanderers were very similar to you and me. Although they lacked everything we'd consider a modern convenience, such as wheels or corrective eyewear or probiotic yogurt, these stalwart folk lived off the land, the rivers, and the bounty of coastal waters. They surely had songs, traditions, religions, technology, explanations, and tales of their own history. Likely they had tales of the creation of the world and its various plants, animals, and, of course, people. They would have been just as curious as we are about the wheeling stars, the shifting seasons, and the origin of all things. Plausibly, there was the occasional ingenious and inquisitive person who, after dropping and rolling some stones, or carefully observing the world in other ways, drew some conclusions about the way the world works, which we, more than 100,000 years distant, would consider, if not correct, certainly along the right track. However, lacking the ability to write or any clearly developed notions of geometry or mathematics, their insights would barely, if at all, persist beyond their own reckoning. Fast forward nearly all the remaining time between us and them, and we find the Greeks, and at the same time, the Indians, people from the Indian subcontinent, around 500 BC. They started to develop a formal and documented philosophy about the machinations of nature. This set of ideas was, thanks to the written word, able to wend its way through subsequent history, and with much greater fidelity than oral tales could have ever managed. It is these people, just a brief step from modernity, who began in earnest the pursuit of science, or what many have called natural philosophy. The written word was key to this development, as was the invention of mathematics, or discovery, depending upon your point of view on that particular topic. The written word was key to this development, as was the invention of mathematics. For the first time in 200,000 or more years since our species evolved, people could learn from past generations with a fidelity only possible through the written word. They could possibly correct their mistakes and contribute to a growing library of knowledge about the cosmos. This venerable but still accumulating knowledge about the structure, form, interactions, rules, and patterns in nature constitutes the hard-won substance of scientific discovery and theory. Because we will be exploring scientific ideas together, we'd best be clear about what the term science even means. I cannot give you a perfect definition. In part, this is because definitions of complicated things are always a bit slippery. from a philosophical as well as a linguistic standpoint. In part, it's because science means different things in different contexts. But I can give you some thoughts about a useful definition. In brief, science encompasses at least the following: a set of methods for discovering facts about the building and explanations of reality, a growing collection of verifiable observations concerning every phenomena and all objects that exist, a corpus of ever-improving and self-correcting knowledge about everything real and possible, a disciplined methodological framework used to specify and carry out controlled experiments, an occupation whereby one studies some aspects of reality. The purview of science encompasses both non-human reality, such as physics, astronomy, chemistry, biology, etc., and human-centric reality, archaeology, psychology, political science, etc., with some overlap between different fields. Finally, science is a sociological practice of exchanging ideas and validating or debunking other people's insights and ideas. People work in science, they do science, learn science, produce scientific results, and often do so within scientific communities. The distinguished and highly accomplished Nobel Prize-winning physicist Ernest Rutherford once declaimed, he was British, so, all science is either physics or stamp collecting. Most think that he meant that physics, which concerns itself with matter and energy and forces, underlies everything else that's real. However, this sentiment seems to belittle scientific pursuits other than physics, not to mention philatelists. The scientific study of the influence of color on human mood, or the study of ecological systems, to name two examples, are very far removed from the realm of particles and forces and fundamental physics. But these studies are clearly scientific. In my opinion, all science starts with stamp collecting. All science starts by recognizing that one thing or experienced or witnessed phenomena is not like another. Lightning isn't like water. Dirt isn't like fog. Snakes aren't like puppies. Note, however, that some things can fall into multiple human-defined categories. For instance, both snakes and puppies are vertebrates and animals, but only one of them is a reptile. Sometimes we decide that something in nature fits into a category, whereas previously we excluded it. For instance, no scientist would have put mold into the category of medicines until a particular strain of the mold penicillin was found to have antibiotic properties in 1929. All this falls solidly into the subcategory of positivist inquiry that concerns itself with definitions. With our innate human capability to categorize and generalize, we seek to separate classes of objects or events into separate conceptual piles or sets. Next, we ask what the things in a set have in common, or what distinguishes members of one set from another set. This first important step is synonymous with Rutherford's stamp collecting. Only after we've categorized events and things grossly can we begin to further refine their distinguishing characteristics and measure their properties in a systematic way, likely creating subcategories in the process. Thus, the very act of assigning names and categories to natural objects and occurrences is part of science. Thus, the honor of philatelists is restored. Once we've narrowed our focus to some set of related things, we can begin to poke at them, observe them in different situations and angles and with different senses. We begin to relate them to other things, build conceptual models about how to define them ever more clearly, and ascertain what properties they have and how they interact, constructing an ecosystem of knowledge. Once we get to this stage, we've moved beyond stamp collecting. You may think that nearly every science has progressed far beyond stamp collecting phase, but that's not so. Every time there's an academic debate about what to call or name something, it constitutes a purely human endeavor to get some particular category more precisely defined. Unfortunately, nature doesn't always cooperate with our desire to draw precise boundaries around categories. A given cloud can be somewhat cirrus-like and somewhat cumulus-like, but might not fall into either specific category. A hominid fossil can be somewhat Australopithecus-like and somewhat human-like, but not definitively either. A body of water can be partly sea-like and partly lake-like. An animal can be bird-like and also mammal-like. A small, cool star can be a bit planet-like and a bit star-like. The examples are numberless. Nature tends to confound our artificial human desire to draw clear boundaries by smearing things out along continuums. This fact inspires endless fiddling and debating among those tasked with naming natural things. Richard Dawkins calls it the tyranny of the discontinuous mind. Science entails human efforts to build models about what is real, about verifiable and consistent things that are consistent with everything else we know in nature. In other words, science is about everything. That's an ambitious goal, I'll admit. However, each of us, scientists or not, is looking for answers to all sorts of questions almost all the time. Mike, is there any comment or question so far on?
No, I haven't seen anything yet.
Okay. We cannot help but try and make sense of the world. This has immense practical benefits. One would quickly find oneself in peril if one failed to build a basic model of gravity and falling down, or heat and fire, or the danger of river currents and overpowering waves. Each of us must build some sort of representation of the universe in our mind in order to survive. In that sense, we are all scientists. Our senses provide us with information about ourselves and the universe. In more precise terms, we begin by perceiving stimuli. These stimuli are turned into information flows within our brains, carried by biochemical electrical currents. Our brains, via mechanisms that to date are imperfectly understood, use this information to construct models about whatever it is we perceive. We can then consciously or unconsciously manipulate these models to gain comprehension of what we saw. Beyond that, we can also manipulate these models to predict what might occur in the future. Science is just the formal way of building ever better models, with each successive iteration providing an ever-improving agreement with reality. Evidence is the fuel that feeds the engine of scientific inquiry. Evidence separates superstition and myth from reality. Evidence is a precious thing with rare and clear exception. When I talk about evidence, I mean physical evidence. There are other sorts of evidence. Testimonial evidence or word-of-mouth evidence can be exaggerated or fabricated. As anybody who's played the game of telephone knows, even conscientious intents to relay information accurately and honestly can result in significant alteration of an original message. Anecdotal evidence is a special kind of testimonial evidence where only one or a very small number of persons make claims about an event or entity they observed, especially a rare or extraordinary claim. Anecdotal claims generally don't count as trustworthy evidence until verified. As the saying goes, extraordinary claims require extraordinary evidence. This dictum was first documented by the philosopher David Hume, who wrote, "In our reasonings concerning matter of fact, there are all imaginable degrees of assurance, from the highest certainty to the lowest species of moral evidence. A wise man, therefore, proportions his belief in accord with the evidence." Documentary evidence are evidence of claims, accounts, records, and testimony captured in a transferable record like paper, clay tablets, photographs, audio recordings, or digital documents. The trustworthiness of documentary evidence depends upon several factors, including, importantly, the credibility of the source, and especially upon independent corroboration by persons who are not in collaboration. Physical evidence, the best kind of evidence in terms of its objectivity and persuasiveness, is again, physical evidence. Physical evidence results from the independent action of natural processes. Almost everything that happens creates physical evidence, from the fingerprints left behind on a touched object to the seasonal layers of silt on a lake bed, to the flash of light accompanying a meteor, or the sound waves emitted by a spoken voice. Physical evidence is a manifestation of real things happening in the real universe. Some physical evidence is transient. Some physical evidence is easy to fake. Physical evidence provides a consistent, independently verifiable, and usually repeatable assessment of some quality, process, attribute, or response. One of the most, one of the most esteemed organizations in the world is Britain's Royal Society. This organization, chartered by King Charles II in 1660, is the oldest scientific society in the world. Its full name is the Royal Society of London for Improving Natural Knowledge. I'm especially fond of its motto, nullus in verba, which is Latin for don't take anybody's word for it. This motto of this most esteemed society of scientists highlights the value placed on physical evidence because it warns us away from mere hearsay. It explicitly recognizes the distinction between a mere claim and a demonstrated fact. It implicitly emphasizes observation and experimentation, the hallmarks of modern science. These provide a means for obtaining physical evidence, which is the most trustworthy sort we have. The motto also warns us against deferring to the voice of an expert and implies that we should demand verification by means of clear evidence. Some of you have seen this before. I've used it in other talks. Mathematically speaking, an asymptotic curve, we are perfectly justified in claiming certainty as long as we're willing to live with the triflingly small possibility of being surprised and mistaken. We can speak without equivocation, unless we're pressed to admit that to a challenger that our certainty is only vanishingly close to 100% absolute, and that no evidence has ever gainsaid it. However, we can be completely confident about some scientific claims, such as the fact that planets orbit the sun due to gravitational effects, even if we don't yet perfectly understand a fundamental theory of quantum gravity. We can agree with complete certainty that table salt is composed of crystals formed by matched pairs of sodium and chlorine ions, that clouds consist of water vapor, that human beings are animals, and so on. I'm an inveterate scientific realist, or I strive to be. I am unflaggingly confident that reality exists, independent of my conception of it, and that many human-created scientific models and theories do a good, sometimes great job of describing reality. I'm confident that the universe is comprised solely of matter, motions, forces, fields, and a handful of elementary particles, often assembled in astoundingly complex ways. In philosophy, the search for what is real comprises the study of ontology. In a complementary way, the philosophical study of epistemology seeks to clarify how we learn, know, and create conceptual models within our own consciousness. There are physicists who ascribe to anti-realism, which is the notion that all we ever do is describe our interactions with nature and not nature itself. Another philosophy not uncommon among physicists is instrumentalism. According to this, scientific models and calculations tell scientists what future measurements and values their instruments will likely yield. And no claims are made about what is real, only what is measured. Nature is never discordant with itself. That bears repeating. Nature is never discordant with itself. It has no paradoxes, only mysteries. If some scientific model is contradicted by observation, then all or part of the model is mistaken, or the observation is. Similar to the way any one object will only ever travel in one direction at any moment, all of nature's laws and facts will always lead to one real physical outcome. Whenever a seeming paradox is encountered in science, it's an invitation to discovery. Inevitably, something human beings have done or thought or built into a model is mistaken. It may not be possible to disprove some things, but in a limited context, we can prove and disprove many things. I can prove there's no platypus in this room right now, although I'm not going to do so, because I need to stand here. But I cannot prove there are no platypuses in any rooms or that there has never been a platypus in this room, though I can assert it's highly improbable. That's because a single, verifiable, contrary violation of an assertion can disprove it. But anybody's lack of evidence is not an evidence of lack, to repeat an old philosophical chestnut. Lest you or I get too bound up by this frustrating logic, we could recognize a distinction between logical proof based upon deductive reasoning and scientific implausibility or plausibility based on inductive reasoning or abductive reasoning. Abductive reasoning is like inductive reasoning, but it adds the notion of obtaining the simplest and most likely explanation for a conclusion. So it's a little more stringent. I cannot prove in a strictly logical sense that I will never spontaneously morph into a platypus, because I cannot see the future. But I can assert with great confidence that such an eventuality is implausible. To such an extent, it's essentially indistinguishable from impossible. The essentially in that last sentence leaves a little bit of wiggle room for the future universe to prove me wrong. But for every practical context outside of a pedantic discussion about logic, it's safe to conflate extremely implausible with impossible. One of the problems scientists and science communicators often have is that their awareness of the tiny cracks in our logical certainty makes them use language that sounds like equivocation. They say something like, "It's virtually certain," or "It's nearly impossible," or "It's extremely implausible," or even, "There's no known way that could happen." To many listeners, that makes it sound like the scientists lack confidence. Instead, she is simply being careful and precise. My own opinion is that scientists should avoid equivocation when the only reason they are using such language is due to the purely logical problems with deduction versus induction. When the bulk of evidence and precedent is on one side, one should feel free to speak confidently about what does exist and what is or is not possible, and save the equivocation for debates with philosophers. A scientist can make claims with confidence as long as she freely admits that some future evidence might gainsay a particular claim. The impossibility of disproving the existence of a thing or an occurrence because evidence cannot be found is quite different from cases where contrary or contravening evidence is found. The logical fact that every scientific law or theory is provisional requires that all such human ideas be, in principle, disprovable. If there's no conceivable way, no experiment that could disprove an assertion, it's not a scientific assertion about reality, but a dogmatic one. Some, such as the philosopher Karl Popper, have even gone so far as to claim that science is a continuous effort to disprove what we think we know or assert. Another name for disprovability is falsifiability. In principle, every scientific theory, model, hypothesis, and conclusion is falsifiable. Popper's idea of the importance of falsifiability brought an important notion into the philosophy of science. At a minimum, it helped scientists and philosophers realize that a theory which isn't in principle falsifiable through observation is dubious at best. But he went too far. It's preposterous to think that scientists the world over toil, for example, over swinging pendulums, rolling balls, falling apples, and colliding particles of matter in an earnest attempt to find that one time when Newton and Galileo and Schrödinger got it wrong. The scientific method you learn in school is also problematic. In the past few decades, for example, the importance of Bayesian reasoning has been recognized. This statistical and reasoning method helps formalize the process of making plausibility claims based on evidence and an accumulating pile of both confirmatory and refuting evidence. The traditional scientific method is better thought of as a set of principles that help provide guidance than as a recipe. For example, it leaves important things out, such as the let's poke it with a stick method. It leaves out the danger of biases and the importance of peer review, corroboration, and consensus. These are social aspects and the focus of the remainder of my talk. I mentioned previously that science is a social activity. No scientist in the modern era starts from scratch. They all build upon discoveries, evidence, and predictive models of scientists who preceded them. Not only that, nearly every one of the big questions about how, what, where, and when of nature have been very nearly perfectly answered by our era. Speaking of asymptotic approaches to perfection, there's a funny old definition of an expert: a person who knows more and more about less and less until they know everything about nothing. In the modern era, every scientist, indeed every person, can only know a fraction of all that is known. That means that even with tremendous effort, each of us remains safe from knowing nothing. Although I must admit, it seems to be a double-edged curve, such that those who expend no effort to learn science are at least as likely to be perfectly ignorant and on a quest to know nothing. However, by working together, we can collectively manifest almost preternatural genius. I mean, just look at Wikipedia. My key point is that science and the accumulation of documentation of knowledge is a community activity. A great example, in my opinion, is to be found at the beginning of the 20th century. This is a picture of the attendees at the 5th Solvay Conference in 1927. This was a time when single educated human minds could discover fundamental profundities about nature. Especially it was a time when the foundations of three great edifices of modern science were laid: quantum mechanics, relativity, and astrophysics. Nowadays, such opportunities seem quite rare. Now it seems advances in science seem more incremental. For example, this is a This is a photograph of many scientists and engineers who worked on the Large Hadron Collider experiment detector that helped to discover the Higgs particle. This scientific paper had 5,154 authors announcing the discovery of the Higgs from the CMS experiment. And highlighted here is a member of our congregation at the church and a science enthusiast. In fact, he's a PhD physicist, Dr. Michael Albro. The history of modern science from the 19th century until now is unfortunately replete with stories of prejudice, exclusion, and bigotry. Women and non-white persons have been excluded, overlooked, and under or unrewarded in terms of prizes, recognition, and even pay. These practices are repugnant to me, and I'm happy to see significant progress is being made against these medieval or Victorian-era misogynistic and bigoted practices. Collaboration isn't mentioned in the canonical scientific method. Neither is confirmation or the importance of removing biases through activities like double-blind studies. But insofar as science is a human endeavor, it's subject to human failings. Not just the psychological failings of confirmation biases, fallacious thinking, and so on. Relevant to today's topic is a subject, science, is subject to social influences. Prizes, peer review, for example, are all critical to the sociology of science, whether your article is published or not, based upon an assessment of somebody who may have their own biases, is a part of this picture. The social practice of science also involves providing a living to scientists. Chasing tenure is quite challenging and has at least as much to do with the number of prizes and especially the money you bring in to an institution. And it's not very much related to the quality of your teaching or how well you inspire new generations of curious minds. Again, in my opinion, this is problematic. There are other social norms in science that might be considered problematic. I am not a scientist, but I'm an avid reader and fan of science. I believe the expectation that science writing will be dryly devoid of emotion, including delight and surprise, is sad, if not off-putting, to younger generations of erstwhile students who approach the universe with awe and wonder only to have it siphoned and their delight attenuated until they produce stultifyingly musty prose. At least writers of popular science are encouraged to enliven their product, to make it marketable. Another norm is the focus on original research. Hardly is there an incentive to reproduce an experiment, especially in the social sciences, once a putative discovery has been announced. Even criticizing an accepted scientific finding can be dangerous. There is one woman in the picture from the Solvay conference, and that is Marie Curie. But there's nobody who is not a Caucasian. And again, I think largely this has to do with biases in the scientific study at that time and subsequently. But also there's a pipeline issue with the lack of opportunities for education and research that have found their way into the non-European world, at least at this juncture in 1927. But Marie Curie was so phenomenally talented that she could not be ignored.
And she had a supportive husband who
Right.
collaborated with her, and
Yep.
a few other things probably had to come into effect, some we may know about and some not.
Right. There's a wonderful, I don't remember if it's a movie or a miniseries, I think it's on Netflix, about Marie Curie.
Oh, yeah.
And I really enjoyed it. I think it's Netflix. In this picture of the scientists who worked on the discovery of the Higgs, there are more than 70 countries represented. So the parochial nature and the insular nature of science is beginning to deteriorate, and I think that's good for all of us. You know, when you're judged by your peers or subject to publication, it can put pressures on you such that your ability to teach and inspire is far less remarked and rewarded. So back to what I was reading. Hardly is there an incentive to reproduce an experiment, especially in the social sciences, once a putative discovery has been announced. Even criticizing an accepted scientific finding can be dangerous. For instance, the brown eyes, blue eyed social experiment by Jane Elliott, where she told a class of young children that those with blue eyes are smarter and stronger and better behaved and deserve more cookies in recess time, and then told the student with brown eyes that they were failures and stupid. Anyway, that study has been written about in textbooks and referred to widely as a method to combat racism in children. Instead, subsequent research and interviews with the experiment's childhood subjects has shown that instead it was a great way to traumatize children. A book I've mentioned several times in the past is entitled Galileo's Middle Finger. It relays lessons about science that treads on supposedly sacrosanct ideas and the sometimes terrible consequences visited upon scientists who have dared to do so. I can give you examples if you want. Finally, I want to join the chorus of science communicators and scientists who decry the perils of far-left postmodernist activism in relation to science. A philosophy even more ubiquitous and at least as perilous within the humanities. Among other things, this philosophy justifies the notion that all explanations and all points of view are equally valid. For example, the anthropologist Elizabeth Weiss has written about how her field has been hampered by what she sees as an unreasonable deference to the mythology of native peoples, who may want to impose their rituals on human remains or scientists that are 3,000 years removed from them in time, predating any extant tribe. No known tribe has a lineage in archaeology or cultural anthropology that goes back more than 3,000 years. And yet when we find remains of a human in the Americas that is 9,000 years old, extant tribes lay claims to those remains as ancestors of their tribe and subject to their rituals and beliefs. The author gives examples of times when female anthropologists are prevented from working at sites now today in the USA because of their gender, or a rule that insists women cannot eat with the men while on tribal lands. I worry that censorship and curtailment of free inquiry is at least as likely to originate from the ideological left as the right. The pursuit of science is antithetical to the notion of off-limits and sacred topics. Everything should be able to be questioned with respect, humility, and earnest curiosity.
I believe she was the scientist that was taken off of an archaeological
Right.
dig. She was removed from it because of complaints by Native American people and relative to some of the points you were saying, right?
Right.
And she's a very well-known, a great
Highly
scholar. in this-
esteemed,
yeah, highly
yeah.
esteemed scholar of this, but there was a little bit of misogyny about
Right.
it because she's a woman, and also other aspects of it in terms of you shouldn't just be studying this thing because this is a human and needs
Right.
to be treated with respect to our community.
Now, I've never interviewed an anthropologist, but I've read books written by anthropologists, and I've seen documentary series and whatnot. And one of the things that I believe is that anthropologists are highly, highly respectful of the fact that they are dealing with human remains, and archaeologists are dealing with human constructs. They're very careful to behave in an honorable and respectful way. And prejudice based upon mythology is generally sneered at and discarded or discounted when it comes to Christian beliefs. Like if you I'm making this up, but maybe if you find some bones somewhere in Europe, maybe you should, anoint it with holy water or something. But maybe that would be a recommended practice by some Christian sects. Well, we laugh at that. Scientists don't engage in that sort of ritual. And yet, we become so super sensitive to the demands of certain niche cultures that we're willing to make allowances for mythology and practices that can be quite harmful and deleterious to science and actually insulting to practitioners such as women scientists. I recommend this episode of the Michael Shermer Show. You can find it wherever you find podcasts. It's an extended interview with Elizabeth about some of these issues. It's episode 248 of the Michael Shermer Show.
But there's some aspect, you're talking about, it seems like you're saying that this is something that occurs on the left and on the right. I don't see exactly how this is somebody from a left perspective or a progressive perspective. I would tend to feel from my own prejudices that they would be more respectful and more willing to listen to what people are saying, and because they are, maybe they accommodate those things, but I'm not sure that that's a bad thing either, right?
Well, as you acquire the disposition such that you equate the factual content, the truth claims, and the relevancy of anybody who makes an assertion, you dilute anyone who has proof, right? It's the false equivalency thing that you could see on news shows where you get 99.98% of climate scientists say that global warming is caused by humans, and you have one scientist who may be an economist in Sweden who says, I disagree. And so you sit down a climate scientist with this one other scientist and you have them debate for half an hour or an hour. That's a false equivalency. I believe, and others that I have read and listened to, have this idea that the left, the philosophical and ideological left, is more likely to say, no, we need to embrace all points of view as being equally valid. And when it comes to evidence about the natural world or about natural history, such as the migrations of primitive peoples, there is a verifiable set of facts about what happened and when. and ritual and preference doesn't factor into that.
I know when I was a kid, there was a camp that my family used to go to, and they actually had in this one building, they had what they said was an ancient Native American, they probably said it was an Indian skeleton in there, and us kids could go in there, and it was one of these glass cases, and you could actually open it up, and like we'd dare each other to touch the bones and stuff like that. You know, and so there is an aspect of courtesy and so on for other cultures.
I think most scientists would not approve of having those remains accessible to the general public or to children to fondle.
Yeah, and some is just we've grown, I think, in time to have a more respect for
Right.
other cultures and so on, and you know, and maybe because left-leaning people might be more inclined to say they have a respect for other cultures, then they can be said that they're bending over too much and they're willing to do the things that you're saying they're doing.
Right.
But I'm still
Well,
have
like
trouble.
banning this woman from a site because one of the things she talks about is she was menstruating, and one of their practices is that a woman in such a state should not be allowed in a certain area, right?
Got to go into the red tent for a week.
Yeah, something like that. You know, just preposterous, nonsensical kinds of ways to behave. But because, in my opinion, and in some opinions I've read, because the tribe is threatened culturally by the overwhelming, overbearing nature of Western white society, you know, they want to give special deference to every rule and ritual that the tribe wants to hold up. And I think I think you err, it's not just erring on the side of caution, I think it's erring on the side of being preposterous.
I mean, a lot of these cases have gone to court battles and
Right.
things like that. They
Like
haven't just
Kennewick
been-
Man.
Yeah.
Yeah, I disagree. I don't think Kennewick Man should have been reburied. It was remains from 10,000 years ago, thereabouts, having no plausible relationship to any extant tribe. But just because it was found in a particular geography, it'd be like, I don't know, digging up a skeleton of a Neanderthal in some town in England that's Anglican, and saying, well, now the Anglican Church has to take over these remains and treat them like it would any Anglican, deceased person. It's just absurd.
Yeah, I believe in the Kennewick Man case and in others, they've gone through DNA testings and things like that have, and I'm not knowledgeable enough to know exactly what the results were. But
Well, certainly that individual and other individuals will have some relationship, even from a genetic standpoint, to peoples that are extant today. But that relationship, you might find the same thing with Cherokee from Florida, and Seminole from Louisiana, and Navajo from the desert Southwest. It could be that all these people have a genetic relationship to Kennewick Man because he lived 10,000 years ago and people spread out.
yeah, I mean, I would say that people that are Native Americans or historically Native Americans have some level of vision in their mind that they're more related to this person
Oh,
than
certainly.
we are.
Yeah.
And potentially genetically able to be shown that too. And so if they decide that this has some aspect, not only with how a 10,000-year-old man has been treated, but how our ancestors were treated 150 years ago, they may feel like they need to go to bat for that person to stand up for their cultural heritage, even though it may not be exactly theirs or discernible that way.
Yeah, I've found that I have some disagreement with people whose opinions I have a deep respect for on this and related matters. Another one that comes up is the Mauna Kea telescope, the construction of telescopes on Mauna Kea, and the fact that many native Hawaiian peoples are adamantly opposed to that because they consider it a sacred mountain. It really is a part of my intellectual disposition and intellectual DNA, if you will, that there's no such thing as sacred. Now, there are things that are worthy of protection and respect, artifacts from ancient world that we shouldn't demolish. You know, up until the 18th and 19th century, whenever they found Roman artifacts or ancient artifacts, the tendency was to just tear them apart and reuse the building materials, right, rather than preserve them as being instructive about the human legacy. So I'm very much on this side of preserve, protect, study, and cherish, but I'm not on the side of that mountain is sacred, so you can't walk on it or you can't build a telescope. The benefits of exploring the universe from the unique characteristics that that mountain at that place on the globe possesses, I think, far outweighs. And we should include Native peoples. We should include them in the building, in the running of the telescope, in the operation of the facility, offer scholarships. You know, I'm all for educating people, but I'm not typically on the side of let's stop exploration because my ritual doesn't allow for it, or my belief that there's a sacred spirit there doesn't allow it. That's my personal view on it. Let me finish my reading, and then we can... So in another example, a vast majority of human beings, albeit with few known exceptions, and there are some, we're all built with cells that contain either an X and an X chromosome or an X and a Y chromosome. The first indicates a female sex and the latter a male sex. And yet biologists can get in trouble these days for talking about the biological sex of persons and cells. Again, my opinion, and there's going to be people who disagree with me, that is preposterous. Gender identity is a separate issue from biological sex for most people. Granted, biology is fuzzy, and there are fuzzy lines in between sexual dimorphism as well. All of these are examples of the way social conventions and norms influence science and the discussion of science, and even what science is allowed or encouraged to be pursued. There are many more I suspect we can talk about, and that's what I have written. Okay. A lot of that was an excerpt from this book. This is my book. It's finally published. It's available on Amazon. It's entitled A Wanderer's Journey Through a Wonderful Cosmos. And I have one copy available for sale. Mike, I have a copy for you too to replace an early draft you got that had some formatting errors and whatnot.
I've been reading in that, and it's been fascinating. Thank you so much. Yep. Yeah. Based a lot upon your first scheduled long-term talks with us of the cosmos and
right.
Talks in there, and yeah, it's phenomenal. Very well written, very well explained, and very inspiring. Yeah.
Thank you. So, any more discussion? We can probably go another 5 or 10 minutes. Any more discussion about anything I've covered in today's topic that anyone would like to contribute?
We're going to try to use the microphone just so that we don't have to repeat questions up at the front. Maybe make sure it works right now.
Yep.
That's a work.
Wow, it works.
Please spit into the microphone.
I don't know if you're aware of the study that's been done that the American Indian is a unique genetic group. Evidently, of course, there was a country, if you will, in Northeast Asia, and for something on the order of 40 or 50,000 years, the people lived there, and this is the group of people who ultimately immigrated from there and throughout the New World. And so if you look at all of these original peoples of both North and South America, they are genetically a unique group.
Interesting.
Which would tend to go along with the point that somebody who's a Native American descendant living nowadays would use that explanation as a reason to feel connected with Kennewick Man or the early people that crossed through Pangaea.
Not specifically one tribe, right? That was my point.
But of course it has nothing to do with tribes.
Right.
Just like we Scots, who are very proud of the fact that we belong to a particular clan, and it has nothing to do with, and now.
Anybody else have a comment or question or disagreement? I hope that I take disagreement very amiably.
We could do a study on that.
Yeah, poke me with a stick.
There are some questions in cosmology, for example, dark energy and dark matter. And how would you handle those in your definition? Because when you talked about it before, you talked about finding real things.
Yeah.
And right now, I guess there's some concern whether these are actually real or not. And then there are other questions in cosmology, and you've studied a lot of this, is that, you know, from the Big Bang, you can, right now, science can only take us back so far. So how do you handle those kinds of, you know, those kinds of instances in
Right.
your modeling?
So the book I've written delves into those specific examples fairly in depth, but succinctly, it gets back to Bayesian reasoning and arguments about plausibility and what we can plausibly extrapolate from what we are very confident about into realms where many guiding principles like the conservation of energy and the conservation of momentum and conservation of charge, et cetera, where the things we are certain about, we justifiably remain certain that those same rules will apply in domains that we cannot directly access. And so it's what I call a justifiable extrapolation from what is known to what is unknown. And there's a really clear example of that, in my opinion, and that is what happens at the core of the sun, right? No instrument that we could ever conceivably construct made out of atoms, and atoms are all there is, no instrument we could construct could ever go into the core of the sun and check the ambient temperature and pressure and the rate of nuclear reactions, right? And yet, by collecting evidence from the surface of the sun about the color and the temperature and the composition of the sun and the convective cells and whatnot, we can extrapolate from what we do know and the evidence we gather combined with other evidence that may come from particle accelerators, and we can extrapolate reasonably and justifiably about what happens in the core of the sun. So I think that same reasoning can be applied, for example, to make plausibility arguments about certain multiverse claims. For dark matter and dark energy, for dark matter specifically, there are really, really compelling pieces of solid evidence that dark matter is stuff that's out there and real. An alternative explanation has been, well, maybe our equations of gravity are just screwed up. Maybe Einstein's equations and maybe Newton's equations of gravitational effects just don't apply at the scale of galaxies and galaxy clusters. Let me give you one piece of evidence. There are X-rays, high-frequency X-ray light, that is detected from the environs of galaxy clusters. X-ray light happens because electrons and other charged particles are accelerating very energetically. If you calculate the amount of visible matter in those galaxy clusters, you add up all the possible contribution from the stars and clouds of gas and dust that constitute galaxies, you see that the matter that is moving so fast it can emit X-rays and gamma rays, that matter would quickly dissipate from the galactic cluster of galaxies, hundreds of galaxies. The matter surrounding that in a halo would waft off into the wider universe, except it must be bound gravitationally to the cluster. And in order for that to work out, the cluster must contain much more matter than we can see in gas and stars. So that's just one piece of evidence that says dark matter is a real thing and not just a modification of our models of the way gravity works.
There may be evidence of something that we decide to call dark matter because we don't know enough about it to even give it a better name than that, but there is some levels of evidence here.
Right.
knowledge out there that then you can start hypothesizing from.
Yeah, a better name for it is invisible matter, because matter is visible because it interacts with light. That's what makes everything visible. So this is matter that doesn't interact with electromagnetic fields. It doesn't produce, absorb, or filter light. So it's invisible matter. That's a better name. And then dark energy gets back to the rate of expansion of the universe, and something called the cosmological constant. And all of those have solid, scientific, justifiable reality, even though we can't stick a thermometer in some spot in space and measure the amount of dark energy per se. Just because we can't directly observe it doesn't mean that indirect evidence, like from the core of the sun, makes a persuasive case for what its properties are. And it likely has properties we don't know anything about. There could be a whole dark sector of interacting dark matter particles of different species, but we have no way to know that yet. Any other questions or comments? Anything from online?
No, it was kind of quiet online today.
How many people?
6
All right.
right now.
Well, thank you all. I will be back in 2 weeks because you're going to be in Italy. Take lots of pictures.
Yeah,
And I think
drink a lot of wine.
I'm going to talk more. I'm trying to decide between two topics. One of them is scientific toy models. I call it toy models. I have, over the course of my reading and thinking, developed several simplistic models of ways to look at things in the world, and I thought it might be valuable to share some of those with you and get some feedback about why they're broken or why you might find them useful. So that's one of the ideas. The other is to delve more into what I was talking about earlier, the distinction between experimental, observational, and theoretical science, but I could maybe defer that one. And then around the third week of October, Dave, my husband, is going to talk about Halloween in the context of science. We're still trying to figure out, he's still trying to figure out what form that'll take.
We
Right.
did stuff around Easter time with resurrection science a
Right.
few years, and so we were kind of batting ideas around, and Dave and you came up with this concept.
Yeah.
Yeah.
All right, thank you all. See you next time for a
Okay.
Science Sunday.
Check out Amazon for Scott's book, Wanderer's Journey Through a Wonderful Cosmos.